All right, let's get right into it. Welcome to today's Explainer, where we're tackling a really pivotal topic in software engineering, system building. You can think of this as the absolutely crucial automated step where all the scattered pieces of a giant puzzle finally snap together. We're going to explore exactly how we transform raw source code into a working, executable program. It's a fascinating process, and by the end of this lecture, you'll have a really comprehensive understanding of how modern software systems are assembled. Here's a quick look at our agenda for today. We'll start with an introduction to system building, then look at the 3 system platforms, dive into continuous integration in practice, see what happens when continuous integration fails, explore how to minimize system recompilation, and wrap up with a comprehensive lesson summary. Let's get going. Section 1, Introduction to System Building. Let's lay down our foundational vocabulary. What exactly do we mean when we talk about building a system? Well, officially, system building is defined as the process of assembling program components, external data and software libraries, and then compiling and linking these to create an executable system. Okay, but let's break that down if you're hearing this for the very first time. Compiling simply means translating the raw source code that a human wrote into machine-readable object code. And linking, that's connecting that newly translated code with external libraries so the whole program actually works. Now, because modern systems are incredibly complex, we're talking massive amounts of information, this entire process absolutely has to be driven by automated build tools. Doing it by hand? No way. It's practically impossible and highly error-prone. To handle all that complexity, we rely heavily on automated build tools. And, these tools don't just compile code, they do the whole shebang. They automatically generate build scripts, which are basically configuration files telling the system exactly what needs to be built. They integrate seamlessly with your version control system to grab the right versions of your code. They figure out how to minimize recompilation, saving literally hours of time. Plus, they link everything into that final executable program, automate your testing by running tools like JUnit to make sure the build isn't broken, and they even churn out detailed reports and system documentation. So just to recap real quick, system building is this automated assembly, compilation, and linking process completely managed by tools.
Right, moving on to Section 2, the 3 system platforms. Because now that we understand the tools, we really need to know exactly where all this code lives.
Take a look at this. This perfectly illustrates the 3 distinct environments we deal with. First up, on the far left, we have the development system. This is your private workspace, your personal laptop where you write code and run local tests. Then, sitting right in the middle is the build server. Think of this as the central heavyweight server that holds the definitive master version of the project. This is where everyone checks their code in. Finally, over on the right, we've got the target environment. This is where the software actually lives and executes in the real world. Now hold on a second, because we need a massive misconception alert right here. A lot of students fall into the trap of thinking, hey, the program works on my laptop, so it's going to work perfectly everywhere, right? Actually, scratch that. The development platform is not always the target environment. Imagine you're writing software for an embedded system, like a digital watch or a mobile phone. That target environment is tiny, with completely different hardware and a different operating system compared to your powerful dev laptop. Or think about a massive enterprise system that needs huge databases that couldn't possibly fit on your local machine. The reality is, code often exhibits different behavior on the target platform, which is exactly why rigorous testing across these environments is absolutely crucial. Okay, so we know what a build is, and we know the 3 platforms. Let's look at Section 3, Continuous Integration in Practice. If you take nothing else away from this part, remember this dramatic golden rule of software engineering: never break the build. When you check your code into that central build server, it cannot, under any circumstances, cause the whole system to fail. This rule is designed to put a bit of psychological pressure on developers, right? You're held accountable. So naturally, you're going to be very, very reluctant to deliver new components without testing them thoroughly in your own private workspace first. It forces good behavior and stops the team from wasting hours fixing a completely broken master build. In agile methodologies, the goal is to make lots of small changes and rebuild the system frequently. This flow maps out the continuous integration journey. It shows how developers pull the mainline system from version control, build and test it locally, make their updates, and then retest. Only after it passes locally do they commit to the central server. And we often use tools like Jenkins here, which automatically trigger a server build the very second a developer finishes an update. It's all about getting that immediate feedback. Let's walk through these exact steps slowly, because this is the golden flow of continuous integration. Step 1. You extract the definitive mainline system into your private workspace. Step 2, build and test it locally, just to make sure the baseline actually works before you start messing with it. Step 3, make your specific code changes. Step 4, and this is vital, retest locally. You have to be 100% sure your code passes those private tests. Step 5, check it into the build server. And finally, step 6, the server builds and runs its own tests. If it passes, fantastic, your changes become the new definitive baseline. If it fails, well, the developer has to recognize the fault and fix it immediately. So, long story short, CI is all about constantly integrating and testing small changes to catch bugs early.
But what happens when reality clashes with theory? Let's get into Section 4, when continuous integration fails.
Continuous integration sounds like a dream, right? But we have to compare it against a fallback approach called the daily build. Why would CI ever fail? Well, imagine you're working on a massive software system that literally takes 8 hours just to compile. You simply cannot rebuild that system multiple times a day for every tiny change. Or what if the software requires highly specialized hardware on the target platform that you just don't have sitting on your desk? You can't exactly test it locally. In these tricky situations, that agile ideal of CI just goes out the window, and teams have to fall back to the daily build approach. So here is how the daily build acts as a really practical solution for those massive systems. Step 1, the team sets a hard deadline, let's say 2 p.m. Everyone has to submit their code by that exact time. Step 2, a massive, comprehensive compilation and linking process kicks off and runs overnight when the servers aren't busy. Step 3, the next morning, this brand new built system is handed straight over to the testing team. And step 4, the testers run their suite of tests and report any faults back to the developers to fix for the next daily cycle. It's a very structured, reliable rhythm for those super complex environments. All right, quick recap. We've covered CI for rapid changes and daily builds for the massive stuff, but both rely on compilers, and compilation eats up time. So, Section 5, minimizing system recompilation. To minimize that build time, our automated tools have to intelligently link the source code, the actual text we write, with the object code, the machine instructions. Look, they really don't want to recompile the entire system if you only tweaked one single file. To pull this off, the tools associate a unique signature with each source file and its corresponding compiled object file. By comparing these signatures, the system knows exactly what changed and only recompiles that specific code. And there are two main ways to generate these signatures: timestamps and checksums.
Let's contrast these two methods carefully, because this is a really vital concept. Modification timestamps are pretty basic. They just check the time and date a file was saved. So if your Java source file was last modified at 1703, but your compiled class file was modified earlier at 1658, the system recognizes the source code is newer and recompiles it. Simple enough, right? But source code checksums are much, much safer. A checksum calculates a totally unique mathematical hash based entirely on the actual contents of the file. If you change even one single character, the whole checksum changes. This is vastly superior because it relies on the actual data, not just a clock. Plus, it allows multiple versions of object code to exist simultaneously, which means you can run parallel compilations and save an immense amount of time.
Okay, we're on the home stretch. Let's dive into Section 6, Comprehensive Lesson Summary. We've covered a ton of ground today. Here is your ultimate study sheet. First, the definition. System building is the automated process of assembling, compiling, and linking components and libraries to create an executable program. Second, remember the 3 platforms: development, build server, and target environment. And never forget that code can behave very differently once it hits the target platform. Third, continuous integration, or CI, is the practice of frequently building and testing small changes driven by that golden rule: never break the build. Fourth, if a system is just too massive for CI, teams prioritize a daily build that compiles overnight. And finally, to minimize recompilation time, build tools use signatures. Checksums, which hash the file contents, are definitely the way to go over simple modification timestamps because they're safer and allow for parallel compilation.
We've seen today just how intricate and rigorous this whole automated system building process has to be. But I want to leave you with a bit of a provocative thought. If building a system perfectly on a quiet day is this complex, how on earth do we manage the chaos when customers start demanding thousands of new changes, bug fixes, and feature updates? That very question is going to lead us directly into our next critical topic in software engineering: change management. Thank you so much for joining this explainer, and I really look forward to exploring that fascinating challenge with you next time.